This is Sarah Wilkinson from the University of Guelph-Humber and Humber College. This video is going to explain how to use the ACSM formula to predict performance. In a previous video, I showed you how to use the ACSM equation. For this video, we're going to use the ACSM equation along with VO2 max and lactate threshold to predict performance in a race. So let's start with a question. Let's say Bernard has a VO2 max of 52 mL per kilogram per minute and a lactate threshold of 58% of his VO2 max. The question is, how long will it take him to run a marathon on a flat course? If you're given that a marathon distance is 26.16 miles and that 1 mile per hour is 26.8 meters per minute, and you're given the ACSM equation for running, you can solve this. I'm going to take a few minutes to show you how to do this. The first thing we need to review is lactate threshold. So you can see here on the y-axis is blood lactate concentration. That's an indication of how much lactic acid is being produced by the muscle and how fast it's being cleared. On the x-axis is exercise intensity. So we would expect that as exercise intensity increases, so does the production of lactic acid and therefore the appearance of blood lactate. However, at a certain point, at a certain intensity, there's an exponential increase in blood lactate concentration. We call this the lactate threshold. What it indicates is your ability to maintain aerobic metabolism, to produce ATP using oxygen. Below the lactate threshold, you can do this. Above, the person has to produce ATP so quickly that they start to rely on anaerobic glycolysis, and therefore lactic acid is produced faster than it can be cleared. When this happens, the person will not be able to exercise for a long period of time, as the hydrogen ions accumulated in the muscle will cause pain, inhibit enzymes, and inhibit cross-bridge formation, so muscle contractions cannot occur as readily. In this example, Bernard's lactate threshold is 58% of his VO2 max. That is, at 58% of Bernard's VO2 max, he starts to produce lactate quicker than he can clear it, and therefore he will not be able to maintain a workload above 58% of his VO2 max for very long. So we want to know what the actual VO2 is at his lactate threshold. We know his VO2 max is 52 mL per kilogram per minute. So we want to know what is the VO2 at lactate threshold. In order to solve this, what we're going to do is we're going to take the percent at lactate threshold and multiply it by his VO2 max. So his VO2 at lactate threshold is going to be equivalent to 58% of his VO2 max, and we're going to write this as a decimal, and we're going to multiply it by his VO2 max, which is 52 mL per kilogram per minute. Therefore, the VO2, where lactate starts to accumulate in his blood, is going to be equivalent to 30.16 mL per kilogram per minute. We're going to now use this number to be able to figure out what speed is going to be equivalent to a VO2 of 30.16. If we had access to a metabolic cart, we would be able to actually have him run and measure what VO2 is equivalent to that speed. However, let's assume we don't, so we're going to have to use the ACSM formula. There is some inherent problems with this, and so we're going to have an answer that's approximate. So recall that a person can maintain a pace equal to or lower than their lactate threshold. Once they pass their lactate threshold, lactic acid production results in hydrogen production, which will inhibit performance. So we already know that his VO2 at lactate threshold is 30.16 mL per kilogram per minute, and that we have the ACSM equation here. We're going to rearrange the ACSM equation in order to figure out what speed requires an oxygen consumption of 30.16. So we know VO2, we want to figure out speed. Initially in the question, I said he's running it on a flat course. So here we would substitute percent grade being 0. And if you remember from elementary school math, any number multiplied by 0 is equal to 0. So we're going to be able to get rid of this part of the equation because speed times 0 times 0.9 is 0. So we'll be able to write it out like this. So 30.16 is equal to speed times 0.2 plus 3.5. And we're going to be solving for speed. To do this, we're going to use some basic algebra. So again, here's our same formula. Now this time, instead of having speed in meters per minute and that making it a little hard to visualize, I'm going to say that speed in meters per minute is equivalent to S. So I can rewrite this being 30.16 is equal to S times 0.2 plus 3.5. In order to visualize this a little bit easier, I'm just going to rearrange this a little bit. So I'm going to just take 30.16, remove the units, I'll put them back in at the end. Okay. I'm going to put 0.2 here, S beside it. S times 0.2 is the same as 0.2S. And I'm going to add 3.5. So this makes it look very similar to solving a basic algebra problem. We need to isolate S. So in order to do this, anything that's added or subtracted, we're going to need to do first. Then we're going to need to do anything that's multiplied or divided. So your basic PED mass. So let's isolate S. If I subtract 3.5 from both sides, I'm going to be able to isolate 0.2 because 3.5 minus 3.5 is equal to 0. So I can rewrite this. 30.16 minus 3.5 is equal to 26.66. And because 3.5 minus 3.5 is 0, that's going to be equal to 0.2. I have to do one more step to further isolate S. If I divide both sides by 0.2, on the right side, any number divided by itself is going to be equal to 1. And I'm going to divide the left side by 0.2. So S is going to be equal to 133. Now if you recall, I said earlier S is equal to speed in meters per minute. We figured out the speed, now we're going to add the units back in. So the speed that is going to elicit a VO2 of 30.16 will be running at 133.3 meters per minute. Let's put that back into our graph. So earlier we said we need to find out what speed is going to elicit a VO2 of 30.16, and now we've just found that out. It's 133.3 meters per minute. So that's the maximum speed Bernard can run his marathon at. If he starts to run any faster, he's going to start to accumulate lactate, and that's going to inhibit his performance. So, to review, we know that a person can maintain a pace equal to or lower than their lactate threshold. We figured out his lactate threshold, and we've just figured out the speed that would elicit that VO2. However, a marathon is measured in miles. We've got his speed measured in a metric number. So we're going to need to convert this to how fast he can run in miles per hour. In the initial question, I gave you a conversion factor that 1 miles per hour is equal to 26.8 meters per minute. So let's do that now. So we've got his speed in meters per minute, and we need to convert it to miles per hour. So we're going to use some conversion factors to do this. If I have meters per minute on the numerator, I'm going to put it on the denominator here, and I'm converting to miles per hour. I know there's 26.8 meters per minute in 1 miles per hour, and that of course meters per minute are going to cancel out. So I'll get my answer in miles per hour. So in order to do this, very simple, I take 133.3, multiply by 1, which is the same number, and divide by 26.8. So that I know 133.3 meters per minute is equivalent to 4.97 miles per hour. So that's how fast Bernie or Bernard can run. So let's put this back into our graph. So we know that at his lactate threshold, he'll be running at a speed equivalent to 4.97 miles per hour. So far we figured out his VO2 at lactate threshold is equivalent to a speed of 133.3 meters per minute, which is the same as 4.97 miles per hour. We know that a marathon is 26.16 miles, so we need to know how long this is going to take. So let's start off with how long he's going to run for, which is 26.16 miles. We need to convert this to hours. So miles will cancel out, and we know that he's running at a pace of 4.97 miles per 1 hour. Miles cancels out, and we're going to get our answer in hours. So if we take 26.16 miles, divide by 4.97, we get an answer of 5.26 hours. Now, when I say I'm going to meet you in 5.26 hours, that doesn't make a lot of sense. We normally measure things in hours and minutes. So we need to take that 0.26 and convert it to minutes. So let's take 0.26 hours. We're getting rid of hours. We need to figure out how many minutes that is. We know there's 60 minutes in 1 hour. The units cancel out, and we're going to get our answer in minutes. So 0.26 times 60 gives you 16 minutes. So our final answer in terms of how long it's going to take Bernie to run a marathon will be 5 hours and 16 minutes. So let's go back and revisit the question and talk about what we found out. The question was, Bernard has a VO2 max of 52 mils per kilogram per minute and a lactate threshold of 58%. The question was, how long will it take him to run a marathon on a flat course? We used the ACSM formula. We figured his VO2 at lactate threshold. We then figured out what speed he had to run at to achieve that. And then, knowing that marathon was 26.16 miles, we figured out it would take him 5 hours and 16 minutes.